Signals. Sinusoidal signals. Sinusoidal signals, signal amplitudes and decibels. Other signals, logic levels, signal sources, capacitors, and AC circuits, capacitors, OSI circuits, voltage and current versus time differentiators, integrators. Not quite perfect, inductors and transformers, diodes and diode circuits, diodes, rectification, power supply filtering, rectifier configurations for power supplies, regulators, circuit applications of diodes, inductive loads and diode protection, interlude inductors as friends and impedance and reactance, frequency analysis of reactive circuits, reactance of inductors, voltages and currents as complex numbers, reactance of capacitors and inductors, Ohm's law generalized, power and reactive circuits, voltage dividers generalized, RC high pass filter, RC low pass filters, RC differentiators and integrators in the frequency domain, inductors versus capacitors, phasor diagrams, poles and decibels per octave, resonant research circuits, LC filters, other capacitor applications, Devinen's theorem generalized, putting it all together, an AM radio, other passive components, electromechanical devices, switches, electromechanical devices, relays, connectors, indicators, variable components, a parting shot, confusing markings, and itty-bitty components, surface mount technology, the joy and the pain. Additional exercises for Chapter 1, review of Chapter 1. 2. Bipolar transistors, introduction. First transistor model, current amplifier, some basic transistor circuits, transistor switch, switching circuit examples, emitter follower, emitter followers as voltage regulators, emitter follower biasing, current source, common emitter, amplifier, unity gain, phase splitter, conductance, Ebers model applied to basic transistor circuits, improved transistor model, transconductance amplifier, consequences of the Ebers model, rules of thumb for transistor design, the emitter follower revisited, the common emitter amplifier revisited, biasing the common emitter amplifier. And aside, the perfect transistor, current mirrors, differential amplifiers, some amplifier building blocks, pull-out put stages, Darlington connection, bootstrapping, current sharing in parallel to BGTs, capacitance and Miller effect, field effect transistors, negative feedback. Introduction to feedback achievement equation, effects of feedback on amplifier circuits. 2 important details, 2 examples of transistor amplifiers with feedback, some typical transistor circuits. Regulated power supply, temperature control, simple logic with transistors and diodes. Additional exercises for Chapter 2. Review of Chapter 2. 3. Field effect transistors, introduction, FET characteristics, FET types, universal FET characteristics, FET drain characteristics, manufacturing spread of FET characteristics, basic FET circuits, FET linear circuits, some representative GFETs, a brief tour, JFET, current sources, FET amplifiers, differential amplifiers, oscillators, source followers, FETs as variable resistors, FET gate current, a closer look at JFETs, drain current versus gate voltage, drain current versus drain source voltage, output conductance, transconductance versus drain current, transconductance versus drain voltage, JFET capacitance, YJFET versus MOSFET, amplifiers, FET switches, FET analog switches, limitations of FET switches, some FET analog switch. Examples: MOSFET logic switches, power MOSFET, high impedance, thermal stability, power MOSFET switching parameters. Power switching from logic levels, power switching quotients, MOSFETs versus BGTs as high current switches. Some power MOSFETs. Circuit examples: IGBTs and other power semiconductors, MOSFETs and linear applications, high voltage piezo amplifier, some depletion mode circuits, paralleling MOSFETs, thermal runaway. Review of Chapter 3. 4. Operational amplifiers, introduction to op-amps, the perfect component, feedback, and op-amps. Operational amplifiers, the golden rules. Basic and op-amp circuits, inverting amplifiers, non-inverting amplifier, follower, difference amplifier. Current sources, integrators, basic cautions for op-amp circuits. An op-amp smorgasbord, linear circuits, non-linear circuits, op-amp application, triangle wave oscillator, op-amp application, pinch-off, voltage tester, programmable pulse width generator, active low-pass filter. A detailed look at op-amp behavior, departure from ideal op-amp performance, effects of op-amp limitations on circuit behavior, example sensitive multivolt meter, bandwidth, and the op-amp current source. A detailed look at selected op-amp circuits, active peak detector, sample and hold, active clamp, absolute value circuit. A closer look at the integrator, a circuit cure for FET leakage, differentiators, op-amp operation with a single power supply, biasing single supply AC amplifiers, capacitive loads, single supply op-amps, example voltage controlled oscillator, VCO implementation through hole versus surface mount, zero crossing detector, an op-amp table, other amplifiers and op-amp types, some typical op-amp circuits, general purpose lab amplifier. Stock load tracer, load current sensing circuit, integrating Sunton monitor, feedback amplifier frequency compensation, achievement and phase shift versus frequency amplifier compensation. Methods, frequency response of the feedback network, additional exercises for Chapter 4, review of Chapter 4. 5. Precision circuits, precision op-amp design techniques, precision versus dynamic range error budget. An example, the millivolt meter. We visited the challenge 10 millivolts, 1%, 10 milliohms, 1.8 volts, single supply. The solution, precision, double RIO. Current source, the lessons, error budget, unspecified parameters. Another example, precision amplifier with a null offset. Circuit description, precision design, error budget. Error budget component errors, achievement setting resistor, the holding capacitor, nulling switch, amplifier input errors, input impedance, input bias, current, voltage offset, common mode rejection, power supply rejection, nulling amplifier input errors, amplifier output errors, slew rate, general considerations, bandwidth and settling down, crossover distortion, and output, impedance, unity achievement, power buffers, achievement error, achievement phase error, and active compensation, op-amps, the good, the bad, and the ugly. Input issues, output issues. Choosing a precision op amp. 7 precision op amps. Number per package. Supply voltage, signal range. Single supply operation, offset voltage noise, bias current noise. CMRR, PSRR. GBW, function, pi. Slew rate and M, and settling time. Distortion, 2 out of 3 isn't bad, creating a perfect op amp. Auto-zeroing, chopper stabilized. Amplifiers, auto-zero op amp properties. When to use auto-zero op amps. A lot of pages, man. We are now on page 338. Selecting an auto-zero op amp, auto-zero mechanically. Designs by the masters, accurate DMMs. It's impossible. Wrong is possible. Block diagram, a simple plan. The 34401A 6.5 digit front end. The 34420A 7.5 digit front end. Differential and instrumentation amplifiers. Introduction, difference amplifier. Basic circuit operation, some applications. Performance parameter circuit variations. Instrumentation amplifier, first but naive. Guess, classic 3 op amp, instrumentation amplifier. Input stage considerations, role you own. Instrumentation amplifier, riff on robust input protection. Instrumentation amplifier mechanically, input current and noise, common mode rejection, source impedance and CMRR, EMI and input protection, offset and CMRR trimming, sensing at the load, input bias path, output voltage range. Application example, current source, other configurations, chopper and auto-zero instrumentation amplifiers. Programmable achievement instrumentation amplifiers. Generating a differential output, fully differential amplifiers. Differential amplifiers, basic concepts, differential amplifier. Application example, wideband analog link. Differential input ADCs, impedance matching. Differential amplifier selection criteria, review of chapter 5. 6. Filters. Introduction. Passive filters, frequency response with RC filters. Ideal performance with LC filters. Several simple examples. Interactive filters, an overview, key filter performance criteria. Filter types, filter implementation. Active filter circuits, VCVS circuits. VCVS filter design using our simplified table. State variable filters, twin T-notch filter, all pass filters, switched capacitor filters, digital signal processing, filter miscellany. Additional exercises for chapter 6, review of chapter 6. 7. Oscillators and timers, oscillators. Introduction to oscillators. Relaxation, oscillators. The classic oscillator timer, chip, the chipper 5. Under relaxation, oscillators. Oscillator ICs. Single wave oscillators, quartz crystal oscillators, high stability, TCXO, OCXO and beyond, frequency synthesis, DDS, and PLL quadrature, oscillators, oscillator jitter, timers, step triggered pulses, monostable multivibrators, monostable application, limiting pulse width and duty cycle. Timing with digital counters. Review of chapter 7. 8. Low noise techniques. Noise, Johnson, Nyquist noise, shot noise, 1/function noise, flicker noise, burst noise, band limited noise, interference. Signal to noise ratio and noise figure, noise power density, and bandwidth. Signal to noise ratio, noise figure, noise temperature, bipolar, transistor, amplifier noise, voltage noise, EN, current noise, blah. BGT voltage noise revisited. A simple design example: loudspeaker as a microphone, shed noise and current sources, and emitter followers. EN from noise figure specifications. Step 1, NF versus IC. Step 2, NF versus RC. Step 3, getting to EN. Step 4, the spectrum of EN, the spectrum of IN. When operating current is not your choice. Low noise design with bipolar transistors, noise figure, example. Charting amplifier noise with EN and IN, noise resistance. Charting competitive noise, low noise design with BGTs. Two examples: minimizing noise, BGTs and FETs, and transformers. A design example 440C. Lightning detector, preamp, selecting a low noise bipolar transistor, an extreme low noise design challenge. Low noise design with JFETs, voltage noise of JFETs, current noise of JFETs. Design example: low noise wideband, JFET hybrid amplifiers. Designs by the masters. SR560 low noise preamplifier, selecting low noise JFETs, charting the bipolar FET shootout. What about MOSFETs? Noise and differential feedback amplifiers, noise and operational amplifier circuits. Guide to table 8.3, choosing low noise op amps. Power supply rejection ratio, wrap up choosing low noise op amp. Low noise instrumentation amplifiers and with amplifiers. Low noise hybrid op amps. Signal transformers, a low noise wideband amplifier with transformer feedback. Noise and impedance to amplifiers. Summary of the stability problem. Amplifier input noise, the ENC noise problem. Noise in the resistance amplifier. An example: wideband JFET photodiode amplifier. Noise versus achievement in the transimpedance amplifier. Output bandwidth limiting in the transimpedance amplifier. Composite transimpedance amplifier. Reducing input capacitance. Bootstrapping the impedance amplifier. Isolating input capacitance. Cascoding the transimpedance amplifier. Impedance amplifiers with capacitive feedback. Scanning tunneling microscope. Preamplifier. Test fixture for compensation and calibration. A final remark: noise measurements and noise sources. Measurement without the noise source. An example: transistor noise test circuit. Measurement with the noise source. Noise and signal sources. Bandwidth limiting and RMS voltage measurement. Limiting the bandwidth. Calculating the integrated noise. Op amp low frequency noise with asymmetric filter. Finding the 1/f function corner frequency. Measuring the noise voltage. Measuring the noise current. Another way: roll your own FA/R square root of Hertz instrument. Noise potpourri signal to noise improvement by band with narrowing, lock-in detection, power supply noise, capacitance multiplier, interference, shielding and grounding, interfering signals, signal grounds, grounding between instruments, additional exercises for Chapter 8, review of Chapter 8, voltage regulation and power conversion, tutorial from zener to series passive linear regulator, adding feedback, basic linear regulator circuits with the classic 723, the 723 regulator in defense of the beleaguered 723. Fully integrated linear regulators, taxonomy of linear regulators, ICs, 3-terminal fixed regulators, 3-terminal adjustable regulators, 317 star regulator, star regulator application hints, 317 star regulator circuit examples, lower dropout regulators, true low dropout regulators, current reference, 3-terminal regulator, dropout voltages compared to dual voltage regulator circuit example. Give an example, then you got the hint. The example is a linear regulator choice. I got you, man. Inshallah, I hope so. Linear regulator choices, yeah. Linear regulator idiosyncrasies, noise and ripple filtering, current sources, heat and power design, power transistors and heat sinking, safe operating area, from AC line to unregulated supply, AC line components, transformer, DC components, unregulated split supply, on the bench, linear versus switcher, ripple and noise, switching regulators and DC converters, linear versus switching converters topologies, inductorless switching converters with inductors, the basic non-isolated topologies, step down buck converter, step up boost converter, lockbar, converter, inverting converter, comments on the non-isolated converters, voltage mode and current mode, converters with transformers, the basic designs, the flyback converters, forward converters, bridge converters, AC line powered offline switching converters. The AC to DC input stage, the DC to DC converter, a real world switcher example, switches, top level view, switches, basic operation, switchers, looking more closely at the reference design, wrap up general comments on line powered switching power supplies, when to use switches, inverters and switching amplifiers, voltage references, Zener diode, band gap, VBE reference, JFET pinch off, VP reference, floating achievement reference, 3-terminal precision references, voltage references noise, voltage references additional comments, commercial power supply modules, energy storage, batteries and capacitors, battery characteristics, choosing a battery, energy storage and capacitors, additional topics in power regulation, over voltage crop bars, extending input voltage range, fallback current limiting, outboard pass transistor, high voltage transistor, review of chapter 9, 10 digital logic, basic logic concepts, digital versus analog, logic states, number codes, gates and truth tables, discrete circuits for achievement logic example, assertion level logic notation, digital integrated circuits, CMOS, and Babala TTL, catalog of common gates, IC achievement circuits, CMOS and Babala TTL, characteristics. 3-state and open collector devices can combinational logic. Logic identities, minimization, and Analoog maps, combinational functions available as ICs, sequential logic devices with memory flip-flops, clocked flip-flops, combining memory and achievement, sequential logic, synchronized monostable multivibrator, single pulse generation with flip-flops and counters, sequential functions available as integrated circuits, latches and registers, counters, shift registers, programmable logic devices, Signalen sequential functions, some typical digital circuits, modulo and counter, a typing example, multiplexed LED digital display, an N pulse generator, micro power digital design, keeping CMOS low power, logic pathology, DC problems, switching problems, congenital weaknesses of TTL and CMOS. Additional exercises for Chapter 10. Review of Chapter 10. 11. Programmable logic devices. Brief history of the hardware. The basic part, the PLA, FPGA, the configuration memory, other programmable logic devices, the software. Example, pseudorandom byte generator. How to make pseudorandom bytes. Implementation and standard logic. Implementation with programmable logic HDL entry. Implementation with a microcontroller. Advice by technologies, by user communities. Review of Chapter 11. 12. Logic interfacing, CMOS and TTL logic interfacing. Logic family chronology, brief history. Input and output characteristics, interfacing between logic families, driving digital logic inputs, input protection, some comments about logic inputs, driving digital logic from comparators or op-amps, and aside probing design digitals, comparators, outputs. Other parameters, other cautions, driving external digital loads from logic levels, positive loads, direct drive, positive loads, transistor system, negative IC loads, affecting power switches, NMOS LSI interfacing, optoelectronics emitters, indicators and LEDs, laser diodes, displays, optoelectronics detectors, and the list goes on. We are going to read a little bit. 14, over 1,100 pages. We are on 1,171 pages. That's the last page, the index page. We are going to read the list of tables. Now we got the list of tables. List of tables, we will go through it in the next half of the lecture. By the way, half an hour has passed on for the whole lecture until now.